Welcome to Brain Vision.
Question number 127 is asking us about a person walking through the desert in the heat of the day wearing a bathing suit. We're asked in the first part of our question to find the rate at which the person's skin is heated up by the following four mechanisms. The first of these mechanisms is the heat of metabolic reactions within the person's body. This is where the energy is converted to heat underneath the person's skin and is acting to heat it up. So that's one of the sources of heat. The second source of heat is the heat from air convection within the desert that's acting to heat up the person's skin. One of the ways in which heat is transferred from one object to another is through convection, and so the person's skin will feel the heat by this method. Another method by which the person's skin will be heated up is by means of solar radiation. The sun in the sky will definitely act to heat up the person's skin very well. And the final source of heat will be the radiation from the environment, the environmental radiation. So we have our four sources of heat impacting this person. Let's see which one contributes most significantly. We're told that the rate at which the person's skin is heated by metabolic reactions is valued at 280 watts, so that rate is given to us. The heat from air convection is given to us via an expression of the following nature. The heat H is equal to K prime times the area of exposed skin, I'm just going to call A sub skin, times the temperature of the air minus the temperature of the skin. We're given values for all of these terms. K prime is valued at 54 joules per hour per degree Celsius per meter squared. The area of skin exposed to the environment by this person wearing the bathing suit is 1.5 meters squared. The temperature of the air is valued at 47 degrees Celsius, and the temperature of the person's exposed skin is 36 degrees Celsius. Performing our calculations, we can cancel out the meters squared and the degrees Celsius from our problem to get our answer in joules per hour. And the heat from air convection turns out to be 891 joules per hour. Now our problem wants all these values in watts. Watts is a measure of joules per second. So we're going to need to convert that 891 joules per hour into joules per second. The way we do that is multiply 891 joules per hour by 1 hour over 3,600 seconds, which is how many seconds there are in 1 hour. Now we can cancel out the hours, and we find that the heat from air convection is valued at 0.2475 watts. So that's the answer for that source of heat. Now for solar radiation, all we need to do to find the rate at which the sun heats up the person's skin is take the energy from the sun per meter squared incident on the person's skin. This is also known as the solar constant, 1400 watts per meter squared, times the area of the person's exposed skin, 1.5 meters squared. We multiply that out, we get a value of 2100 watts for the heat energy coming from the sun. Now, the radiant energy from the environment, the heat from that, can be determined using this expression. H is equal to A times E sigma times T to the 4 minus T sub S to the 4. A is the area of the exposed skin, which we know already. E is the emissivity of the skin, which is valued to 1. And sigma is the Stefan-Boltzmann constant, which has a value of 5.67 times 10 to the minus 8 watts per meter squared times kelvins to the 4th. Notice that in the denominator of this expression, we have kelvins for the units of temperature. So what we're going to need to do, we'll still be using 47 degrees Celsius for T and 36 degrees Celsius for T sub S, but we're going to need to convert them to kelvins for use in that expression there. To do that, all we need to do is add 273 to both of them. So T will become 320 kelvins, and T sub S will be 36 plus 273 gives us 309 kelvins. So now we can begin to plug everything in to find the heat from environmental radiation on this person's skin. It'll be equal to 1.5 meters squared times 1, the emissivity of the person's skin, times the Stefan-Boltzmann constant of 5.67 times 10 to the minus 8 watts per meter squared times kelvins to the 4th times 320 kelvins to the 4th power minus 309 kelvins to the 4th power. That works out to give the heat of radiation from the environment a value of 116.45 watts. So now we have the rate of heat from these 4 different mechanisms. And considering the sun heats up the person's skin at a rate of 2100 watts, we can consider this source of heat the most important. Now, The second part of this question wants us to determine how much the person must perspire in order to maintain a constant body temperature. The way we can figure this out is to know that the heat absorbed by the skin, Q, is equal to the mass of perspiration developed by the person times the latent heat, L. Now, Q, rate of heat absorption, is also equal to the total power of each of these four sources of heat from the previous part of the problem times 1 hour. So we have two expressions for Q. Let's go ahead and equate them to one another. P total times 1 hour is equal to mL. The thing is, we want to find how much this person must perspire in order to maintain this constant skin temperature. So our answer is going to be in a matter of volume. The way we can find volume given mass is using the density equation. Density, denoted by rho, is equal to mass divided by volume. Rewriting that in terms of mass, we can say that that is equal to V times rho. So we can rewrite this expression to say that P total times 1 hour is equal to V times rho times the latent heat L. Now we want to find how much sweat per hour this person needs to produce. So we're going to need to take and divide P total times 1 hour by 1 hour, divide both sides by 1 hour, and then we'll need to get rho times L on the other side. So to figure out the volume of sweat that this person needs to produce in 1 hour, we need to determine the total power, or the amount of heat incident on this person, divided by the density times the latent heat. To find the total power, we need to add up all the heating rates we found in the previous part of the problem, and then divide by the density of water, which we're assuming the perspiration has about that density, times the latent heat of vaporization. And that constant is given to us as well. So we'll just add up all these different sources of heat and the rate at which they act upon our person in the desert here. 280 plus 0.2475 plus 2100 plus 116.45 watts. And that is all going to be divided by 1,000 kilograms per cubic meter. That's the density of water, times our latent heat of vaporization constant, 2.42 times 10 to the 6 joules per kilogram. Dividing that out, we can cancel out the kilograms, and our answer now becomes the volume of sweat this person produces per hour is valued as 1.03 times 10 to the minus 6 cubic meters per second. To get an idea of how much that is, let's convert that into more reasonable units of liters per hour. So to do that, we'll need to take that 1.03 times 10 to the 6 cubic meters per second and multiply by the number of seconds there are in an hour, 3,600 over 1 hour times 1,000 liters per cubic meter. So we can cancel out these units and the value at which the rate at which this person needs to sweat in order to maintain constant body temperature is 3.71 liters per hour. That's quite a lot of sweat they need to produce. The final part of this question wants us to determine what would happen if this person, instead of their bathing suit, wore lighter colored clothing that reduced the surface area of their exposed skin to an area of 0.45 meters squared. Doing this part of the problem, we'll have to redo the calculations for the first part. However, one thing will remain the same. The heat from metabolic reactions within the person's body will still be the same as it was before. The heat from that will still be 280 watts. The heat from air convection, the second listed source of heat, will be different due to the difference in the area of exposed skin. Now, the expression for that source of heat will be equal to 54 joules per hour times degrees Celsius times meters squared times 0.45 meters squared times 47 degrees Celsius minus 36 degrees Celsius. That works out to give this person, the heat on this person from air convection, a rate of 267.3 joules per hour, which again we're going to need to convert to joules per second. So let's go ahead and multiply that by 1 hour over 3,600 seconds. That works out to be 0.074 watts. So that's actually less than if the person were wearing a bathing suit out here. Now, how much will the heat from solar radiation change. Once again, the way we can figure that out is to multiply the value of the solar constant at 1400 watts per square meter by 0.45, the new value of the area of exposed skin. That takes the heat from the sun down to 630 watts. And now the emissivity of the person now will be at a value equal to 0. And finally, there's the heat from environmental radiation. Finally, the fourth source of heat comes from environmental radiation. This will change significantly with this person's new outfit. So now, the expression for H still will be equal to A times E sigma times T to the 4 minus T sub S to the 4th. However, in this situation, the person wearing this lighter clothing will cause the emissivity to drop to 0, so that'll mean this whole expression will just be 0. So environmental radiation won't affect the person's skin at all. Once again, to find the volume of perspiration the person must emit every hour, we'll need to take the total power, P total, which we just get by adding all those heat rates together, divided by the density of water times the latent heat. So now what we're going to get for that will be 280 watts plus 0.074 watts plus 630 watts divided by 1,000 kilograms per cubic meter. Times 2.42 times 10 to the 6 joules per kilogram. And that gives us 3.76 times 10 to the minus 7 meters cubed per second for the volume of sweat this person needs to produce in this lighter clothing. Once again, let's convert that to liters per hour. to get a better idea of how much perspiration that'll be. So take 3.76 times 10 to the minus 7 cubic meters per second and multiply by 3,600 seconds per hour, and then multiply by 1,000 liters per cubic meter. When we do that, we can cancel these out. And this person now will only need to sweat at a rate of 1.35 liters per hour in order to maintain a constant body temperature. So now you can see what makes lighter clothing so much more useful for desert nomads. It reduces the amount of perspiration a person needs to produce in order to maintain a constant body temperature.